Audio Papers presents Does the Inertia of a Body Depend upon its Energy Content? By Albert Einstein. September 27th, 1905. The results of the previous investigation led to a very interesting conclusion, which is here to be deduced. I based that investigation on the Maxwell-Hertz equations for empty space, together with the Maxwellian expression for the electromagnetic energy of space, and, in addition, the principle that the laws by which the states of physical systems alter are independent of the alternative, to which of two systems of coordinates in uniform motion of parallel translation relative to each other these alterations of state are referred. The principle of relativity. The principle of the constancy of the velocity of light is, of course, contained in Maxwell's equations. With these principles as my basis, I deduced inter alia the following result. Let a system of plane waves of light, referred to the system of coordinates x, y, z, possess the energy L. Let the direction of the ray, or the wave normal, make an angle phi with the axis of x of the system. If we introduce a new system of coordinates psi, eta, zeta, moving in uniform parallel translation with respect to the system x, y, z, and having its origin of coordinates in motion along the axis of x with the velocity v, then this quantity of light, measured in the system psi, eta, zeta, possesses the energy L star equals L multiplied by the fraction 1 minus v over c times cosine of phi all over the square root of 1 minus v squared over c squared, where c denotes the velocity of light. We shall make use of this result in what follows. Let there be a stationary body in the system xyz, and let its energy, referred to the system xyz, be big E sub naught. Let the energy of the body relative to the system psi, eta, zeta, moving as above with a velocity v, be big H sub naught. Let this body send out in a direction making an angle phi with the axis of x, plane waves of light of energy 1/2 big L measured relatively to xyz, and simultaneously an equal quantity of light in the opposite direction. Meanwhile, the body remains at rest with respect to the system xyz. The principle of energy must apply to this process, and in fact, by the principle of relativity, with respect to both systems of coordinates. If we call the energy of the body after the emission of light big E sub 1 or big H sub 1 respectively, measured relatively to the system xyz or psi, eta, zeta respectively, then by employing the relation given above, we obtain big E sub naught equals big E sub 1 plus 1/2 big L plus 1/2 big L, and big H sub naught equals big H sub 1 plus 1/2 big L times the fraction 1 minus v over c times cosine phi all over the square root of 1 minus v squared over c squared plus 1/2 big L times the fraction 1 plus v over c times cosine of phi all over the square root of 1 minus v squared over c squared equals big H sub 1 plus the fraction big L over the square root of 1 minus v squared over c squared. By subtraction, we obtain from these equations big H sub naught minus big E sub naught minus open parenthesis big H sub 1 minus big E sub 1 close parenthesis equals big L times open brace the fraction 1 over the square root of 1 minus v squared over c squared, all minus 1, close brace. The two differences of the form big H minus big E occurring in this expression have simple physical significations. Big H and big E are energy values of the same body referred to two systems of coordinates which are in motion relatively to each other, the body being at rest in one of the two systems, in this case system XYZ. Thus, it is clear that the difference, big H minus big E, can differ from the kinetic energy, big K, of the body with respect to the other system psi eta zeta, only by an additive constant big C, which depends on the choice of the arbitrary additive constants of the energies big H and big E. Thus we may place big H sub naught minus big E sub naught equals big K sub naught plus big C, and big H sub 1 minus big E sub 1 equals big K sub 1 plus big C, since big C does not change during the emission of light. So we have big K sub naught minus big K sub 1 equals big L times open brace the fraction 1 over the square root of 1 minus v squared over c squared, all minus 1, close brace. The kinetic energy of the body with respect to psi eta zeta diminishes as a result of the emission of light, and the amount of diminution is independent of the properties of the body. Moreover, the difference big K sub naught minus big K sub 1, like the kinetic energy of the electron, depends on the velocity. Neglecting magnitudes of fourth and higher orders, we may place big K sub naught minus big K sub 1 equals 1/2 big L over c squared, all times v squared. From this equation, it directly follows that if a body gives off the energy big L in the form of radiation, its mass diminishes by big L divided by c squared. The fact that the energy withdrawn from the body becomes energy of radiation evidently makes no difference, so that we are led to the more general conclusion that the mass of a body is a measure of its energy content. If the energy changes by big L, the mass changes in the same sense by big L divided by 9 times 10 to the 20th, the energy being measured in ergs, and the mass in grams. It is not impossible that, with bodies whose energy content is variable to a high degree, e.g. with radium salts, the theory may be sufficiently put to the test. If the theory corresponds to the facts, radiation conveys inertia between the emitting and absorbing bodies. This concludes, does the inertia of a body depend upon its energy content? By Albert Einstein. Thank you for listening.